Welcome back. Today we're going to be talking about optimization and we're going to do specifically an example about inscribed shapes. A right circular cylinder is inscribed in a sphere of radius 3. What height gives the maximum volume? Okay, so first thing I'm going to do is I'm going to draw a picture of the situation. So I'm going to be drawing a sphere. Let's picture that as a 3D sphere, so nice 3D circle there. So use your imagination. And then we have a right circular cylinder inscribed in the sphere. Okay, so now I'm going to draw a cylinder inside the sphere that's going to look like this, like that. And it also says that the radius is 3. Now, when they say the radius is 3, they're implying the radius of the sphere is 3. So that means that the distance from the very middle to the edge, that this distance is 3. And they're wondering which height gives maximum volume. So first, I just want to clarify something. They're not asking about the maximum volume of the sphere. In fact, the volume of the sphere is already predetermined because we already know the radius of the sphere is 3, and that information alone is actually already enough information to find the volume of the sphere. So there's only one possible volume that the sphere of radius 3 can possibly be, right? And so they want to know the height that gives the maximum volume of the cylinder. So what is the volume of a cylinder? Well, recall that volume of a cylinder is equal to the area of the base times the height, which since it's a circular base, that would be pi r squared times the height. But the r we're referring to here, I want to be very clear about this, is not the r of 3, it's that the r, the radius in the actual base of the cylinder, because that's something I see people getting confused about, is they'll plug in 3 and think they have the answer fairly quick. But this radius here that we're referring to is different from the radius that we're referring to over here. All right, so what is our next step? Well, we need to somehow use the fact that 3 is the radius of the sphere in order to help us to narrow this down and get this into just one variable. Now, a very key piece of information is that notice that the diameter of the sphere from here to here is also the diagonal of the cylinder. So the diagonal of the cylinder right here must be 6, right? Because that's going to be the radius times 2 is going to be the diameter. And so this diameter here is 6. And because this is a right circular sphere, we can say, okay, well, let's use Pythagoras' theorem then. We know that this distance here is the diameter, or 2r, and now this r is the same as the r I'm referring to here, and then times the height, which height we also don't know, but we can argue that 2r squared plus h squared is equal to 6 squared, right? This is what's known as Pythagorean theorem. A squared plus b squared equals c squared, where a and b are our legs and c is the hypotenuse. I do have other videos more in detail about Pythagorean theorem if you're interested in that, but assuming that you're already up to date with Pythagorean theorem, I'm going to move forward here. So then I'm going to simplify this, and we're going to get 4r squared plus h squared is equal to 36. And then what I'm going to do here is I'm actually going to solve this in terms of h, just because I think that that might be a little bit simpler. Or actually, no, maybe I won't. Maybe I'll do it in terms of r squared, because we do want the height that gives the maximum volume. We could do it either way, but it might actually be slightly faster to solve for r squared here. So let's try that. I'm going to subtract h squared from both sides to get 4r squared is equal to 36 minus h squared. Then I'll divide both sides by 4 to get that r squared is equal to 9 minus h squared over 4. And now what I'm going to do is I'm going to sub in h squared back into my volume equation. So volume is equal to pi times 9 minus h squared over 4 times h. Next, I'm going to use the distributive property to distribute the pi and the h into here. So we're going to end up with 9 pi h minus h cubed divided by 4 times pi. All right. So next, what I want to do now that we finally have an equation just with volume in terms of h, our height, which is what we're trying to we're going to try to find the height that maximizes the volume. I'm going to take the derivative of the volume next. So let's do that. Volume is equal to, or sorry, the derivative of the volume would be equal to 9 pi minus 3 pi h squared divided by 4. Next, recall that whenever we're optimizing, we want to set the derivative to 0. So I'm going to be doing that. I'll be setting the derivative of my volume to 0. And if I do that, I'm going to get that 3 pi h squared divided by 4 is equal to 9 pi. Then I'm going to just cancel out my pi's. Can I cancel anything else out? I don't think I can, but that's okay. We still have 3h squared divided by 4 is equal to 9. So if I multiply both sides by 4, I get 36. So 3h squared is equal to 36. If I divide by 3, I get that h squared is equal to 12. So therefore, h is equal to the square root of 12, which recall that because 12 is 4 times 3, that would just be 2 root 3. And so therefore, the height that optimizes the volume, the height that gives us our maximum volume, is 2 root 3. And here they didn't give any like dimensions, if it's centimeters, meters, whatever it is. We're actually not sure here. But yeah, so our answer is just 2 root 3 units as the height that gives the maximum volume. Now, as always, if you do have any questions, feel free to leave those in the comment section, and we'll see you for the next one.